Hello everyone, my name is Aarush Gupta and I am presenting this presentation with my groupmate Shubham Dadwal. We are going to talk about the security papers which were presented in USENIC Security 2021 and 2022. Session, we will walk you through a deep comparative analysis of two significant research papers, Cure, presented at USENIC Security 2021, and Composable Cashlets from USENIC Security 2022. Both papers aim to enhance the security guarantees of trusted execution environments, but they approach this challenge from different directions. Cure focuses on redesigning the architectural framework of TEEs by introducing flexible and customizable enclave types that basically supports the isolation across privilege levels, multi-core environments, and IO accesses. Composable cashlets, on the other hand, zooms in on one of the most pressing microarchitectural issues affecting trusted execution environments, cache-side channel attacks. It proposes a cache partitioning mechanism to defend against these threats with high efficiency and minimal performance overhead. This talk will systematically break down each paper, highlighting their problem spaces, proposed mechanism, results, and their real-world relevance. We will examine both side by side to get a clearer picture of how TEE security is evolving. With foundational background focusing on TEE model, how it works and what limitations exist, particularly regarding side channel vulnerabilities. Next, we will present the motivation behind each paper and the problem they aim to solve. From there, we'll delve into their design, discussing architectural decisions, enforcement models, and implementation challenges. We'll look at the performance and security evaluation results from each paper. After that, we will reflect on their strengths and weaknesses, both in technical and practical terms. We'll close with our personal learnings and ideas for how these topics can be better incorporated into academic coursework. The presentation format is side by side so we can understand how both papers complement and differ from each other in vision and impact. Trusted execution environments are isolated sections of a computer's processor that ensures that code and data loaded within them remain confidential and tamper resistant. The key idea is that even if the operating system or hypervisor is compromised, TEE provide a secure bubble for sensitive computation. Talking about our first paper, Cure, builds on this model but critiques existing TEs like Intel SGX and ARM Trust Zone for being too rigid. These platforms support only a single enclave type, typically at the user level, making them unsuitable for more complex or privileged security tasks. Cure proposes to expand this capability by enabling multiple enclaves type across privilege boundaries. Meanwhile, on the other hand, composable cashlets operates under the assumption that even if the TEE architecture seems secure from outside, the hardware it runs on, particularly shared caches, can be a major vulnerability. Cashlets assume SGX-like models are already in place but highlight that because caches are shared, attackers can exploit them using techniques like prime plus probe. So, while Cure innovates on TEE architecture itself, Cashlets innovates within the TEE microarchitectural environment. A cache side channel attack occurs when an attacker, often co-residing on same system, can infer sensitive information by observing how a victim process accesses shared cache. Prime plus probe and flush plus reload are typical techniques where attackers monitor which cache lines are accessed, evicted, or left intact, thereby revealing memory access patterns. These attacks are non-invasive and don't require breaking encryption or even accessing memory directly. They rely solely on measuring access time. Cure acknowledges this threat and proposes to reduce the shared state by isolating caches, memory, and even I/O peripherals at hardware level. However, it does not offer a formal or focused solution to side channel resilience. Cachelets, on the other hand, make side channel mitigation its central contribution. The idea is to break up the last level cache into small slices or cachelets and assign them exclusively to individual enclaves. This physical separation ensures that no two enclaves can interfere with each other's cache state. Their innovation isn't just in dividing the cache, but also in making the partitions composable and dynamic. This allows for more efficient use of cache resources without sacrificing isolation. Pure identifies that existing TEEs are too monolithic and application specific. Intel SGX, for example, supports only user space enclaves and assume that the OS handles peripheral access and scheduling. This limits the usability of SGX in scenarios that require trusted interaction with devices or concurrent multi-threaded processing. For example, you just think of an enclave that wants to process real-time data directly from sensor or network interface. SGX cannot accommodate that due to lack of secure I/O isolation. Cure basically wants to remove these constraints by letting developers choose from different enclave types based on their application needs. Cachelets focused instead on security gap in current enclave system like SGX, which do not protect against cache timing attacks. Although SGX isolates memory, it leaves the shared cache vulnerable. Intel's cache allocation technology and OS level cache partitioning strategies exist, but they either lack flexibility or require trusting the OS. Cachelets' main aim is to fulfill this exact gap by offering enclave-aware, fine-grained hardware enforced cache partitioning. Cure's core contribution is the introduction of three enclave types: user space enclaves, similar to SGX, subspace enclaves, which can isolate code in OS or hypervisor, and self-contained enclaves, which span user and supervisor modes can manage their own scheduling, resources, and devices. This multi-type model allows a system to assign the right kind of enclave for a given workload. It also enables a more modular, flexible TEE architecture that can accommodate future needs. On the other hand, cachelets introduce the concept of splitting the last level cache into small partitions called cachelets. Each cachelet can be dynamically assigned to an enclave and reclaimed later, allowing better utilization. More importantly, the design ensures that no cache line is shared between two enclaves, eliminating opportunities for timing or eviction. Cachelets are managed by a global free list and enforced entirely in the hardware. Chaos architecture is built on RISC-V and involves minimal hardware changes. The processor is extended to include an enclave monitor that manages enclave life cycles, hardware filtering, or peripherals, and support for partitioning CPU cores. The enclave monitor is trusted and minimal in scope. The monitor configures and maintains isolation policies and oversees the creation and tear down of enclaves. This design supports enclaves across privilege levels, which was not possible in existing architectures. Cachelets, meanwhile, modify the CPU's cache controller to include a new indexing logic and replacement policy that binds memory accesses from an enclave to its assigned cachelets. A cachelet allocation table is used to manage cache partitions dynamically. Importantly, cachelets does not trust the OS and relies entirely on hardware to enforce cache partitioning. The mechanism is designed to be scalable and suitable for use in multi-tenant cloud environments.
Thank you, Aarush. From here, I can take over and moving with the slide isolation mechanism. So, Cure provides isolation by assigning exclusive resources to each enclave. A self-contained enclave, for instance, can have its own cores, private DRAM, dedicated cache slice, and even exclusive access to PCLE devices. System bus filtering ensures that no other component can interfere with enclave's memory or I/O. These features collectively eliminate many traditional side channels. Cachelets focuses on microarchitectural isolation. Each cachelet is assigned exclusively to single enclave and is never shared, the system ensures that even speculative execution and eviction logic cannot leak information between cashlets. By doing this, cachelet provides what's called non-interference, a formal property ensuring that one process can observe the behavior of another through shared state. Now we can see the visual representation of both side by side. A good way to visualize cure is to think of three stacked layers. Each layer represents a different enclave type operating at different privilege level. Subspace enclave exists in kernel space, user space enclaves in user space, and self-contained enclaves span both. Each is colored and isolated with filtering logic controlling I/O paths. On the other hand, cachelets can be visualized as a large grid where each block represents a cachelet. Enclaves are assigned one or more blocks, and the blocks are color coded to reflect ownership. When an enclave exits, its block returned to the free list can be reassigned. This dynamic mapping provides scalability and efficiency at the same time. Now, what we observe in the paper, the results. So, Cure evaluation on a real risk V SOC showed that its isolation mechanism work in practice. The system supports secure peripheral access via DMA multi-core enclave scheduling and enclave creation at various privilege levels. The performance cost was 15.33% on average, significant but justified by the security benefits. And with the cashlets were evaluated via simulation and hardware modeling. Sidechain attacks like flush reload and prime pro failed to extract data even when cashlets were in use. Performance impact was under 5% in most cases, and the architecture proved scalable and efficient. Now, the strengths of the paper. Core major strengths are its flexibility, support for secure I/O, and architectural scalability. It lets enclave developers choose the right isolation level for their application. It provides strong hardware enforced boundaries and minimal trusted code base. And with the cachelet strength lie in its precision and formal guarantees. It provides a practical, scalable, and probably secure method of eliminating cache-based leakage with very low overhead. Its independence from OS enforcement make it trustworthy even in hostile environments like the public cloud. Now moving to the weaknesses of the paper. Cure, while flexible, is more complex to manage. Its performance overhead, though justified, might deter adoption for latency critical applications. It's also limited by reliance on risk V, which may limit immediate industry adoption. And with the cashlets are highly effective, but only for cache-based threats. Other microarchitectural channels remain unaddressed. Also, implementing cashlets requires hardware redesign, which means it can't be retrofitted into existing CPUs. And the real world impact. Cure is suitable for advanced systems needing secure interaction with devices like medical machines, smart vehicles, and secure real-time operating systems. And cashlets, on the other hand, are ideal for cloud environments where multiple customers enclave may run on the same server. Their isolation ensures that no customer can spy on another, addressing one of the biggest concern in confidential computing. Now moving to the next slide for like learnings, what we really learned from the papers. Through Cure, we learned that TEE's design is not just about memory isolation, but must involve devices, cores, and even privilege controls. And with cashlets, what it taught us that microarchitecture isolation is just as important and can be achieved with clever hardware software code design. But both papers deepen our appreciation of how modern systems need holistic security, not just software policies, but hardware enforcement as well. And for suggestion and conclusion, to conclude the end, to make these ideas more accessible, we suggest adding practical labs where students can create enclaves of different type or simulate cache attacks, seeing a prime probe attack in action, followed by applying something like cachelets would make the risk and mitigation much more tangible. In conclusion, Cure and Cachelet represent two major strides in TEE security, from system level flexibility to architectural resilience. And at last, I'll say thank you for listening.